It's time to introduce some mathematical models in the course. We have done as much as we could without mathematical models, but to actually price options, we need them. And we will start with simpler models, discrete time models, and then later we will do continuous time models and Black-Scholes. So let's move to the next slide. The simplest one-period model that one could think of is the simplest discrete time model is a one-period model or single period model. So we only have time 0 and time capital T, which I'll probably just call 1, time 0 and time 1. And there is maybe finitely many stock prices, S1 to Sk, and some probabilities Pi, such that probability that the stock price in the future is Si is equal to Pi. Yeah? So this is just a generic description of a one-period model, single period model. I'm going to assume that we have the following assets in the model. We have a bank account, which is denoted B, and at time 0 is going to be normalized to 1, and then B at time 1 is going to be 1 times 1 plus R, so 1 plus R. The interest rate is R in this period. Initial wealth, I'm going to use capital X to denote the wealth of a portfolio strategy. So I'm going to have one investor who is investing in the market, and he starts with X0 amount of money, and the X0 is usually going to be denoted by lowercase x. That's the initial amount of money the investor has. And then the portfolio strategy consists in choosing how many shares of each asset to invest in, and that's denoted by delta I. Delta is the usual usual notation for the number of shares used in option theory. So at the end of the period, the wealth is going to be X of 1. Delta 0 just denotes how much money you put in the bank. You can think of this as the shares in the bank. So it's going to be delta 0 times 1 plus R times B of 1, which is 1 plus R. That's just how much money, initial money delta 0 in the bank goes to, plus number of shares delta 1 in asset 1 times the value of the price of asset 1 at time 1, plus and so on, number of shares in asset n times the value of asset n at time 1. Okay? So there's something called the budget constraint or a self-financing condition, which simply says that there is no extra money coming in or out of my portfolio. I just start with X and that's it. And then all the money stays in and nothing comes in from outside. The way to present this in this single period model is that initial amount of money you have has to be split between all the assets that are available. So there's going to be initially delta 0, B of 0 is just 1, but if it wasn't 1, you just multiply by B of 0. That's the money in the bank initially, plus money in the stock at time 0, plus money in stock 1, and plus money in the stock n at time 0. Yeah? So just split the initial money X0 into all the assets that are available. That's called the budget constraint. Let's see. Next. More notation. Profit loss or gains of a portfolio strategy is simply going to be the difference of what you have at time 1, X of 1, minus what you had at time 0, X of 0. And then I'm going to need notation for discounted version of whatever process Y we are looking at. So Y bar of T, bar denotes discounting. Discounting is simply dividing by the bank account. Okay? That's what discounting really means. So we are going to Y of T over divided by B of T, that's denoted Y bar of T. Okay? More notation, change in price is denoted capital delta Si of 1 of asset I is SR1 minus SR0. That's the change in price over the period in asset I. We could decompose the total gains, profits and losses into profits and losses in each asset. So in the bank account, it's the profit of delta 0 times R, and then in others it's just how many shares times the change in the asset price. All right, and we can also write it this way. We can write x of 1 as x of 0 plus the profits and losses. This is just going to be convenient later on. Now it's just extra notation. Also, let me denote by delta SI bar the discounted version at 1, discounted version of the profit loss. So SI bar of 1 minus SI of 0. I'm not discounting here because there is no discounting at time 0. Okay. So, and G bar is going to be number of shares times the discounted profit losses for all the assets added up together. Okay. And it's an easy exercise to show that discounted wealth in the future is discounted wealth in the past plus discounted profit loss. Okay. Again, this is going to be useful later, not so much now, but later on when we go to multi-period and continuous time models. All right, that was a lot of notation. Let's go on. A multi-period model would simply be starting with the initial stock price which is known today, then goes to some possible stock prices tomorrow with some probabilities, then if it's up here goes to some other possible stock prices in day 2 or period 2. If it goes here, goes to some possible prices in period 2 here and so on. So this is a 2-period model. Right? So that's how it would generally look like. Okay, go on. All right, so this is the same type of notation for a multi-period model. Now I'm going to use T for denoting which period I'm at. Again, I'm going to start the bank account or the risk-free asset at 1, and then it's going to be 1 plus R. Maybe R depends on T, where on the period times the previous, the money in the bank account in the previous time. Number of shares in asset I during the period T minus 1 to T is denoted delta I of T. Okay? That's maybe it's not the best notation in the sense that this is already known, and T minus 1 at the beginning of the period T minus 1 you decide how many shares to hold in asset I. That's denoted delta I of T. So during the T period, okay, that's the notation we use. The wealth process, by definition, the wealth that you have in your portfolio at time T, given that you hold shares delta 0, delta 1, delta n in the assets, is simply you add up all the money you have in different assets, number of shares times the asset, number of shares times the asset, number of shares times the asset, you add them up. Okay? Now there is a self-financing condition for each period. It says there is no extra money coming in and out at each and in any of the periods. So the way to write that is this same thing, x of t, is also equal when I change these t's in the number of shares to t plus 1. Why? Because this is the money during the period t minus 1 to t. Then at t, I'm going to change from these number of shares possibly to some other number of shares, delta 0 t plus 1, delta 1 t plus 1. Okay, and this is the amount I have just before changing, and this is the amount I have just after changing the number of shares in each asset. So this just says at the moment I'm changing from certain number of shares in the assets to some other shares. It has to be the same amount because I don't have extra money. So the money just before changing my positions has to be equal to the total money I have just after changing the positions. That's what it says. Okay? In symbols, this has to be equal to this, but it just means money just before changing my positions is the same as the money I have after changing the positions. All right, that's. I will need this to show you some facts on the next slide. Again, the same notation as before, change in price is capital delta. during the period at t. Gains process is the sum of all the profits and losses in each asset. So now I'm adding over time. I'm adding over S1 to t all the changes, profits, losses in the bank account, profits, losses in stock 1. So I look at the change in price at each period times the number of shares that I was holding in that period. So this is the total gains and losses. And again, it's easy algebra to check that the time t wealth is equal to time 0 wealth plus all the gains or profits and losses up to time t. So again, this is not really that we will need this much for discrete time models, but it's going to help us understand better continuous time models. Namely, let me just kind of tell you about that here to preview. So in continuous time models, I want a pen here. In continuous time models, I will have something like this. X of t is going to be equal to x of 0 plus integral, and then there is going to be a sum over all assets. So, but let's say there is only 2 assets. So it's going to be integral 0 to t. Let's say delta 1 ds1. That's not good. ds1 of u plus integral 0 to t delta 2. So let's say there is 2 stocks and forget about the bank account. Delta 2 ds2 of u. U is just the variable of integration. It's time from 0 to t. Okay? So I'm going to have something like this. It's not quite clear what this means right now, but I will explain that later when we get to continuous time models. But it's just a generalization of this, because integrals in the limit are nothing else but sums of infinitely many parts. So we are going to replace these sums by integrals. Okay? And these, I forgot that deltas also can change with time, so they also depend on u, delta 1 of u, delta 2 of u. Okay? So I'm going to have something like this later, and the way to understand this maybe is to think about this. It's really just adding profits and losses over each, in this case, infinitesimally small intervals, short intervals, and you just add all those profits and losses continuously. Here's the discrete version. This is going to be a continuous version. So this is really why I'm doing this now. Not that I really need this in this generality. It's just kind of help the intuition for later on when we use this model. All right. So discounting, for similarly as before, we will have. Let me just switch here to this. Discounted change in price definition is the same as before. You subtract discounted profit. It's a discounted profit loss. Discounted price at t minus discounted price at t minus 1. So you define discounted gains process as number of shares times this delta change in discounted price. And you can also check that if you discount the wealth process, it's going to be initial wealth plus discounted gains process. Okay? I mean, this may not be that obvious, actually, but let's go to the next slide. We'll see in one example how this works. Okay? So that discounted wealth is equal to initial wealth plus discounted gains. I'm calling them gains, but they might be losses too. Okay. So let's see how this last line works out. So if I have just one risky asset, one stock, and 2 periods, let's check that expression. So what I want to show is that x of 2. Actually, I'm not going to show the discounted version. I'm going to show the non-discounted version. even that is not completely obvious. I'm going to show that x of 2 is equal to x of 0 plus g of 2. That's what I'm going to show, which is equivalent to this last line here. So that's what I want to do. Let's do that. This is just reminding you how we define the change in price. So g of 2 by definition is going to be the deltas during the first interval. So this is in the bank account. Delta 0 in the first interval times the change in bank price in the first interval plus delta 0 during the second interval. So money in the bank during the second interval times the change in bank account during the second period. Plus, and these are the changes in stocks, right? A number of shares in stock during the first period, change in price during the first period, a number of shares in stock during the second period, change in price during the second period. Okay? So what I need to do is actually use that self-financing condition. So self-financing condition, I'm going to use it in this form. Remember, it said if I have delta 1 asset of 1 plus delta of the other asset of 1, the other asset of 1, it's the same as if I move deltas to the next period, 2. Okay? That was the self-financing condition. Before changing and after changing deltas, I have the same amount of money. So if I use that, these two guys, delta of 1 b 0 by 1, delta 1 of 1 s 1, there is one here, there is one here. Right? So I'm going to replace them with these two guys. These two here, I'm going to replace with these two. And I actually have them here, so they're going to cancel. This one is going to cancel this one, delta 0, 2 minus times minus b of 1. And this one is going to cancel this one, delta 1 of 2 with a minus times minus s of 1. Okay? So what is not cancelled is delta 0, 2 b of 2, delta 1 of 2 s of 2, and then from here minus delta 0, 1 b of 0, and delta 1 of 1 s of 0 with a minus sign. Okay? So if you do the algebra, I did quickly now, but you will, if you do this slowly, you can check that you get this. Okay? But this is nothing else. This by definition is x of 2. Okay? Money at time 2 in the bank plus money at time 2 in the stock. That's x of 2. And this is x of 0. Money initially in the bank and money initially in the stock with a minus sign, so x of 2 minus x of 0, okay? Which is the same as x of 2 being x of 0 plus g of 2. So this is what I wanted to show. This is just one simple example. All other expressions that we had can be shown in the same way. Okay, and let me now. So we did very generally discrete time models, any type. In fact, in this course, we are pretty much going to work with only one discrete time model. So what is the simplest possible discrete time model for a stock, which is interesting? By interesting, I mean there is randomness. Okay? Well, the simplest possible one is having two possible values in the future for the stock at each moment. Okay. If I have only one possible, there is no randomness. If I know where it's going, that's really the bank account. That's the risk-free asset, and there is no randomness there. So if I want to make it a stock, if I want to make it risky, I have to have at least two. And that's the simplest possible thing. So this is what the so-called binomial for having two values at each point, or a Cox-Ross-Rubinstein model is. At each point in time, the stock will go to one possible up value and one possible down value. Cox-Ross and Rubinstein are all professors of finance, so this is called Cox-Ross-Rubinstein model. They introduced this model. It's also called CRR model for the initials, so Cox-Ross and Rubinstein. They, in fact, introduced this model historically after Black-Scholes. In fact, a number of years in the 80s, and Black-Scholes was 1973. Even though this is mathematically a much simpler model, in fact, it converges, we'll talk about that later, it converges when the period goes to 0, it converges to the Black-Scholes. So they introduced a simpler model historically after the more complicated model, but that's how it happened. Actually, it's also very helpful. Not only it's simpler for teaching, it's also a way to implement numerically the Black-Scholes model. But we'll talk about that later. All right. So the model formally consists in stock at the future time being equal to stock at the previous time times up factor u, and or stock at the future time is equal to the stock at the previous time times the down factor d. And in principle, you could introduce probabilities for going up and probabilities for going down. So small p is a probability of going up, and 1 minus p is a probability of going down. And there is a condition here that up factor has to be larger than 1 plus r, and 1 plus r has to be larger than d. If you think about it a little bit, this is actually no arbitrage condition. This simply means that the bank is sometimes better than stock. If the stock goes down, the bank is better. And if the stock goes up, the bank is worse. Otherwise, we would have arbitrage. Intuitively, why? Well, because if the stock was always worse than the bank, you would just sell short infinite amount of stock or as much as you can and put all the money in the bank and make arbitrage money. If the stock was always better than the bank, then you would just borrow as much as you can from the bank, put in the stock, and make arbitrage. Okay? So to have no arbitrage, the bank has to be better than the stock if the stock goes down, but worse than the stock if the stock goes up. So that's this condition. We will see it later again. All right, so graphically, binomial tree model, you start with the norms value of the stock S. The probability p goes to s times u, again with the probability p goes to s times u, as u squared. So each time you go up, you multiply by u. Each time you go down, which is with probability 1 minus p, you multiply by d. One feature, one consequence of this is that going up and down is the same as going down and up. If you multiply by ud or du, you get the same thing. Yeah? So we call this a recombining tree. Up and down move brings you to the same value as the down and up move. Yeah, so it looks like this. Yeah. That's going to be the benchmark discrete time model we are going to be pricing options in. Okay, that's it for this set of slides. Thank you.